Okay guys, Unit 2, Lesson 2, remainder theorem continued. So yesterday we really focused, or Lesson 1, we really focused on the long division and synthetic division of polynomials. And now we did introduce this idea of the remainder theorem, but we're going to examine that a little more closely today and look at some proofs and things like that. So by the end of the lesson, you understand what the remainder theorem is, and you can apply it in appropriate situations. So remainder theorem, part 2, right away we're going to review some of that synthetic division. So divide the following polynomial, p at x is equal to x cubed minus 2x squared minus 4 by x minus 2. So using synthetic division, we're going to set it up like this, and the number that goes here is the solution that corresponds with the factor. So remember, if this is x minus 2, then we are looking at x minus 2 equals 0, so we're actually looking at x equals 2. So we would have a positive 2 here, and then we are looking for the coefficients of our terms, and we have to ensure all terms are accounted for. So we have x cubed minus 2x squared, and we're missing our xth term. So we're going to have 0x minus 4. So our coefficients are 1. We don't see it, but we know it's there. Negative 2, 0, and negative 4. Okay, so we have 1, negative 2, 0, and negative 4. So the first step of the synthetic division is always to pull down that first coefficient. It stays, so we've got the 1. And now we're doing 1 times 2, or 2 times 1, it doesn't matter. 2 times 1, and then that's the number that goes here, and it's a 2. And remember, the big difference between synthetic division and real division is that we are adding our columns, not subtracting. And so we have negative 2 plus 2. Okay, so if we're down 2, we add 2, we're at 0. And then we do 2 times 0 and put that number here, which is 0. And now we have 0 plus 0, which is just 0. And then we are doing 2 times 0, which is 0. And negative 4 plus nothing is negative 4. Okay, so what we are left with here is, if we wanted to write out our division statement, if this is p at x, so we know that x cubed minus 2x squared minus 4 is equal to x minus 2 multiplied by, and remember that we take away 1 degree because we divided out a degree 1 from a degree 3. So we know this is x squared. This 0x would be plus 0x plus 0, right? We have those descending terms, but we don't need to write that. So we're just going to write times x squared, and then our remainder is minus 4. If we were to distribute this, we'd have x squared multiplied by x, which is x cubed. We'd have x squared multiplied by negative 2, which is negative 2x squared, and then we'd have our remainder, negative 4. So our left side equals our right side, so we know that we've done it accurately. Now, our remainder theorem states that if this here is x minus 2, then again, we're dealing with positive 2. It's always the opposite. So the remainder theorem states that p at 2 will be equal to the remainder. And we'll look at this in more proper terminology on the next slide. But if we sub in that 2 into the original function, we should get back the remainder. So if we sub in 2 to our original function, so p at 2 is equal to 2 cubed minus 2 times 2 squared minus 4. 2 cubed is 8. Order of operations here, we do 2 to the power 2 first, which is 4, multiplied by negative 2, which is negative 8. And then we have minus 4. 8 minus 8 is 0. 0 minus 4 is negative 4. And would you look at that? It is the remainder from when we did our synthetic division. Remember, that last number also represents the remainder. Okay, so let's look at this in the in general terms, not that specific example. So the remainder theorem states that if p at x, some function at x, polynomial function at x, is divided by x minus b, so we have a factor here. So remember, if we have x minus b, then we're dealing with positive b, x equals b, and the remainder is constant, okay? So meaning that the remainder is not another polynomial degree 1, 2, 3, but it's just a constant. If the remainder is just a number, then the remainder will be p at b. So we take that b value, sub it into the original function, and the function value that we get at p at b will be the remainder if we were to do the long division. So just really, really quickly here, the proof, if we were to consider this information, p at x is some sort of polynomial, we want to divide it, the divisor is x minus b, and when we divide out x minus b, we are left with a quotient, which we'll call q at x, the quotient function, and also the remainder is r. So if we were creating a division statement here, we would say the original function, p at x, is equal to, we're taking our divisor and multiplying it by our quotient function and adding our remainder. Now, what we're saying is p at b, if we sub in that b value, should equal r. So let's see what happens if we sub b into our division statement. So we're replacing x with b. We have b minus b multiplied by the quotient function plus the remainder. Well, b minus b is going to be 0 times the quotient function plus the remainder. 0 times anything is just 0. So this is all 0 plus the remainder, meaning that p at b is and will always be equal to the remainder if the function was divided by x minus b. Okay, so the proof, I'm not going to ask you to replicate that, but just for my why learners, why is that the case? Why does that happen? There's kind of your algebraic proof, and we'll play around with Desmos a little bit after as well. So find the remainder for each division. So we've got this quadratic or degree 2 polynomial, 2x squared minus 3x plus 7. We're dividing it by x plus 4, and all we are asked to do here is find the remainder. So if we want to find the remainder, let's call this function, and I should have already had these here, let's call it f at x. So we are saying we want to know what is f at. Remember, if this is x plus 4, then we're dealing with negative 4. So we want to know what is f at negative 4. So we sub it into our function, negative 4 squared times 2 minus 3 times negative 4 plus 7. And negative 4 times negative 4 is positive 16 times 2 is 32. Negative 3 times negative 4 is positive 12, and positive 7. 32 plus 12 is 44, plus 7 is 51. So let's look at Desmos for this one as kind of check our answer or our proof. What we're saying here is f at negative 4 is equal to 51, and that's also the remainder. Actually, we'll do synthetic division for this one, okay? So let's just take a look at, if we were to use synthetic division, we would have our negative 4 here, and then we would have a 2, a negative 3, and a 7. That accounts for all descending powers. So we have, not negative 2, we have a 2, a negative 3, and we have a 7. So we drop down this 2, we do 2 times negative 4, which is negative 8. We're adding, so we're doing negative 3 plus 8 more negatives is negative 11. Negative 11 times negative 4 is positive 44. And again, we're adding 7 plus 44 is equal to 51, which is our remainder. Okay, so there's just your little proof that shows you, again, if we just sub in the corresponding solution of the divisor, then we end up with the remainder. Okay, so if we were doing this one here, again, we have to figure out what we're subbing in. If the divisor is 2x minus 1, we can set that equal to 0. Use our opposite operations to isolate x, and really the value that we're trying to sub in here is x is equal to 1/2. All right, so a little bit different, but again, now we're dealing with positive instead of that negative, and again, we have to make sure that we're rearranging to isolate our x. So let's just give ourselves a bit of space here. So we're trying to figure out, and again, we'll call this function f at x. So we want to know what is f at 1/2. So we have 4 times 1/2 cubed minus 2 times 1/2 squared plus 6 times 1/2 minus 1. All right, so we have some exponent laws here. When we have a power being applied to a quotient, this is really a quotient, this is 1/2, we have to apply the power to both top and bottom. So the top here becomes 1 to the power 3, which is 1 times 1 times 1, and the bottom becomes 2 to the power 3, which is 2 times 2 times 2. And then we have, again, we have to apply top and bottom. So the top becomes 1 times 1, and the bottom becomes 2 times 2. And then I'm just going to leave this one like this so we can simplify all those fractions in one foul swoop. So if we have a 4 here and an 8 here, we could divide out and we could just make this whole thing 1/2. I'm just going to do this. This would become a 2. So we'd have 1/2. And then over here, same thing. We could divide these out, and we're also left with 1/2. And then here, we could think of it as 6 times 1/2 or 6 divided by 2, but these entire things are going to cancel out, and the whole value of that becomes 3, and then minus 1. And when we go over here, we have 1/2 minus 1/2, which is 0, plus 3 is 3, and minus 1 is equal to 2. So that's our remainder. So if we were to do long division, synthetic division, we would end up with a remainder of 2. Now, remember that that remainder tells us the function value at that point, and so you can always check your work on Desmos. So there's the function we were just dealing with. And to check that function value, there's 2 ways you could do it. You could either say, well, f at x is equal to, and now I want to know what is f at 1/2, and it will tell you f is 2, or sorry, f at x is 2. Or you can draw yourself a vertical line when x is equal to 1/2. Whoops, we got to go down here. When x is equal to 1/2, it will show you this black line here represents the vertical line x equals 1/2. The green is our function, and they intercept right here. When x is 1/2, y is 2. Okay, so different ways you can use Desmos to check your work. Where are we? We're here. Okay, so now let's apply this to some problem-solving questions. So for example, 3, when the polynomial x cubed minus 3x squared plus k times x minus 7 is divided by x minus 4, so remember we're going to be dealing with x is positive 4, the remainder is 29. What is the value of k? So what do we know so far? Well, let's again call this f at x, all right? So what we know is that f at 4 is equal to 29. When we divide this polynomial by this factor, we get a remainder of 29. In other words, if we sub in the solution here, the x equals 4, to the original polynomial, it will equal 29. So we want to know what k is. So let's say 29 must be equal to 4 cubed minus 3 times 4 squared plus k times 4 minus 7. All right, so now it's just algebra, right? We just got to rearrange to isolate. Our variable is now k. 4 cubed is 64. 4 squared is 16 times negative 3 is negative 48. I'm going to rewrite these because we like our coefficient to be in front of our variable, plus 4k minus 7. We can start combining our like terms or rearranging. 64 minus 48 is 9, so we've got 29 is equal to, 64 minus 48 minus 7, is 9 plus 4k, and then we get our 9, our constants all on one side, so we've got 20 is equal to 4k divided by our coefficient to isolate our variable, and we figure out that k is equal to 5, or 5 is equal to k. Okay, so there's one problem-solving application of the remainder theorem. We are going to use the remainder theorem and extend on it in tomorrow's lesson for something called the factor theorem, but the remainder theorem in isolation would be likely used in situations like this where it's a problem-solving question. So let's look at one more question, and in fact maybe you want to pause the video at this point and try this question on your own, or just have a listen to how to set up the question and then attempt it, because really it's just algebra, and then come back to check your work. So for what value of b, okay, so we've got b here, what value of b will the polynomial, so we've got p at x is equal to, here's our whole polynomial, have the exact same remainder when it's divided by x minus 2 or when it's divided by x plus 1? So in other words, when would the function value, when we sub in p at positive 2, when will p at positive 2 be equal to p at negative 1? If we subbed in positive 2 into this function, we would get back a remainder, and we want to know when would that remainder be the exact same if we subbed in a negative 1 for what value of b, what coefficient of this degree 2 term. So pause the video right now and try this on your own, and then come back and check your work. Okay, so hopefully you've attempted this question, but basically it's just straight algebra. So we're subbing in 2, so we've got negative 2 times 2 cubed plus b times 2 squared minus 5 times 2 plus 2 on one side, and on the other side we have negative 2 times negative 1 cubed plus b times negative 1 squared minus 5 times negative 1 plus 2. 2 cubed is 8. Times negative 2 is negative 16. Then we have plus 4b. Then we have a negative times a positive, which is negative. 5 times 2, which is 10, plus 2. Negative 1 times negative 1 is positive 1, times negative 1 again is negative 1, so negative 1 cubed is negative 1. Negative times a negative is a positive, and 2 times 1 is 2, so this whole term becomes 2. Positive times a negative is a negative. 1 times b is just b, or sorry, that's not correct. Negative 1 squared is negative 1 times negative 1, which is a positive, and then positive times a positive, so we've got plus b. Negative times a negative is a positive. 5 times 1 is 5, and we've got positive 2. So we could start simplifying things here. We have negative 16. We're taking away another 10. So we're at negative 26, and then we're adding 2. So we're at negative 24 plus 4b. And over here, we've got 2 plus 5 is 7, plus 2 more is 9. 9 plus b. We want to isolate our variables on one side, so I'm going to take away b from this side, which means I'm going to take it away from over here, and then I'm going to add 24 to this side, which means I'm going to add 24 over here. So what am I doing here? I'm saying 24, writing 25. I'm going to fix that. But you guys get the point. Okay, so those constants cancel out on this side. The variables cancel out on this side. So on the left, I'm left with 4b minus b, which is 3b. And on the right, I'm left with 9 plus 24, which is 33. And then again, divide out my coefficient, divide by 3, and we figure out that b is equal to 11. So in order for the remainder, when dividing by x minus 2 and dividing by x plus 1, in order for the remainder of these to be the exact same, the coefficient of that degree 2 term would have to be an 11. And that also means that the function would have the same function value at these two terms. Okay, so same y value. If we were considering our graph, that this is a degree 3, but at x is equal to positive 2 over here, and x is equal to negative 1, this degree function has the exact same value at those 2 points. So it's a negative leading coefficient, and so it's going to end pointing down. And so I'm just trying to think of an example of maybe what it might look like. It could come up and back down, and then go back up. It could look something like that. It could come through here, and down through here, and then back up, for example. And maybe the value at this point and this point are the same, although it would not be that amount. But you get the point. Those two would have to be the same. Okay, so they wouldn't be zeros. That's not a good drawing, even though they are the same. All right, so that's everything for this lesson. There's some practice questions, and then, of course, make sure you do the exit ticket for this lesson. Okay, have a great day, guys.